Hello again. I am going to apply the hypothesis testing framework to a numerical example. So the example here is about my belief. Suppose that I believe that students spend 30 hours to study for midterm exams on average. So say they take on average 5 classes, and then there will be 5 exams, and then at least spend 6 hours per exam. By the way, we don't have exams. We don't have midterm or final, so uh, it's we are in a very special, uh, unusual environment. So I'm not saying we have an exam. Anyhow, I believe that students spend 30 hours on average on midterm exam, and I want to test if I'm true, if my belief is true or not. So I surveyed 100 students and asked them how much they studied for their midterm exams. And suppose that the sample mean was 31, only 31. So 100 out of 100 students, and the standard deviation was 10. So I collected 100 observations, and their average was 31 hours, and their standard deviation was 10 hours. And we are going to use 5% significance level. So we are going to use this level 5% at the end, but let's focus on the data. So our problem here is I believe 30 hours on average, but the data says 31, which is different from my belief by 1 hour. Then my question is, okay, 1 hour is different, but is that different? Is that difference significant or not? That is my question. So even if the mean is 30 hours, some students may study less than that and other students may study more than that. So when I randomly choose them, I may happen to meet the students who study more than 30 hours, even if the average is 30 hours. So if that's true, 31 could happen by the random error. That's one possible thought. Or on the other hand, you may think 31 hours is too much. So my belief was 30 hours, but observation is 31, which is clearly different. And the difference is not that ignorable. It's significant. So then what we are doing is we are basically trying to see how significant this difference is. The difference between my belief and my observations. So how different they are. That's my question. And we may apply the same framework here again. So let's set up the formal statement of the hypothesis. They can be written as the null hypothesis equals to 30 hours, and the alternative hypothesis equals to is different from 30 hours. So H null and H1 is 30 or different from 30. And in this example, mu, as usual, mu is the population mean. So X is the midterm study hours, and mu is the expected value of that, right? The population mean. And the hypothesis is about the population mean. So we know that the sample mean is the best estimator. So using the same logic, same rationale, same reasons, for the same reasons, we are going to use the sample mean as a test statistic. This is the best way to estimate the true mean, the population mean. So we are going to use the sample mean as the test statistic, right? You remember it is the best estimator. So using that as the test statistic is the best idea. I will not go into the details. It's just mathematical result. So far there is nothing special. I just set up. Now you have to calculate something. So before calculating that, let's think about the null distribution. So we need to understand how X bar, the sample mean, the test statistic, is distributed if my belief is true. My belief was 30 hours. And regardless of my belief, I know that the sample mean follows approximately a normal distribution by the central limit theorem using the CLT. The sample mean follows a normal distribution with the population mean and population variance divided by the sample size, right? We learned it several times in chapter 7, chapter 8. So we are going to use it again and again. So now you must be familiar with this. And on top of this, because we assume that, I believe that students study 30 hours on average, that implies the center mu is 30 hours. So if we assume that the null hypothesis is true, then the center of this normal distribution is 30. And sample size is 100, which is easy. And the variance, the standard deviation squared, and we know that the standard deviation was calculated to be 10. So the variance will be it's squared. So in that, by those plugins, we know the null distribution. So as long as the mean is 30, we know everything about the distribution, right? So the situation is very similar to the binomial distribution. In the binomial distribution, we also knew the full distribution of the test statistic, and we do in this example. So graphically, we know this is the null distribution, and it's centered around 30 hours. 30 hours is my belief. So if my belief is correct, my belief is here, and my observation will be around my belief, somewhere close to the true my belief value. Of course, it will be less likely. It becomes less likely to happen as the value deviates from my belief. So 30 hours is most likely, and 31 and 29, and then 28 and 32. So as it goes away from the mean, probability goes down. So if you have here or here, now you have to suspect if your belief is true or not, right? Suspicious. What is suspicious? Your belief is suspicious. So in the previous example of like free cancellation abusing, a customer is suspicious. More correctly speaking, it is suspicious that the customer's probability equals to 20%. That's a full statistical sentence. And in this case, when you observe something like here or there, very extreme, very different values from 30 hours, then you have to suspect whether your hypothesis is true or not. You have to worry about your hypothesis. Anyhow, it's clear. And in our numerical example, we observed here 31 hours. Excuse me. So you observed here. So when you observe 31 hours out of this distribution, you can think that less likely values are here. Of course, the values have smaller density. And at the same time, you have to think about these guys. Here, on the other side of the distribution, there are also unlikely values in this area, right? So, by the symmetry, 29 and 31 are equally likely. So, as these the value is larger than 31 is less likely than 31, the value smaller than 29 is also less likely than 31. So when you calculate the ranking from the most suspicious, then you have to rank these guys and these guys both on the top. Both extreme values, extremely large values and extremely small values have to be equally on the top. And 31 is ranked after these shaded outcomes, right? So probability on this shaded area, shaded area is the probability of outcomes less likely than your observation, more suspicious than your observation. And that area, that probability, is referred to as the p-value, right? Then how do you calculate that? P-value. So once you have this picture, calculating this probability is not a big deal. You know how to do that. P-value is probability smaller than 29 or greater than 31. So even if we observe 31, you have to consider the other side because they are equally unlikely. So you have to consider, like say, positive errors and negative errors at the same time. So how do you calculate this probability? Standardize. Standardization is taken by subtracting the mean and dividing by the standard deviation. Here, remember the mean. We still believe the null hypothesis, right? We have not proven it wrong. We don't know whether the null hypothesis is wrong or not. Then we believe that's true. So the mean is 30 hours, following our hypothesis, right? So, and standard deviation was calculated. So after all, it's probability outside plus minus 1, which is 31%. So your observation 31 hours, observing 31 hours is from the top 31%, right? If you rank from the most unlikely outcomes, then its rank is 31%, which is reasonably low, lower than, especially low. Before talking about that, as you saw, standardization is also used again, and often we standardize the sample mean separately. Like you don't need to write it every time. So in particular, this guy, this standardized observation, standardized difference. Remember, the standardized sample mean is called the t-statistic. So you may understand it as the standardized difference. So 31 is your observation, 30 is your hypothesis. Their difference is standardized by the standard deviation of the sample mean. And it happened to be 1. It equals to 1. So 1 is in the standard normal distribution scale. So, and instead of standardizing directly from the definition of the p-value, often we calculate the t-statistic first and then plug this into the standard normal distribution. Both are the same, but these steps, you calculating t-statistic and the p-value, is more common. In the end, the answer is the same, 31%. Anyhow, the p-value is the 31%. Now you have to compare the p-value with the significance level, which was 5%. Right? We only allow 5%, and so you are going to reject top 5%, but your observation is at 31%. It's much lower than, less suspicious than your cutoff. So you do not reject your hypothesis. That's the result of this hypothesis testing. In other words, the observation 31 is sufficiently plausible. It's 31%. Sufficiently plausible when the true value was 30 hours. So you don't need to reject your belief. It's plausible. This is like consistent enough with your hypothesis. So that's how you calculate the p-value and make the decision. We are going to do a simple exercise in the next video.